So, hello everyone. Is my screen visible?
Yes.
Okay, so welcome everyone to eighth session of eight problem solving session of analog circuits. So, in this week, we have dealt with circuits like clipper, clamper circuits consisting basically of diodes and BJTs. So we will be solving a few questions on that. So before that, let's touch upon some aspects that were left hanging in the previous class. So first thing, so Subarao is here, right? So you had a doubt in this quadrature phase oscillator, right? Suba, can you hear me?
Yes, sir. Yes, sir.
Yeah. So, so basically, how does this work? Our main circuit. So this is sorry, this is a Wien bridge oscillator. So our main circuit is the core of the circuit is only this much, and how the values of the so we know that the Barkhausen criteria says that the overall loop gain should be equal to 1 for the sustained oscillation. What happens if the A beta is greater than 1? We will have the oscillations go berserk and the system will saturate. And if A beta is less than 1, the oscillations will die out. If this is what happens if A beta is greater than 1. If A beta is less than 1, then oscillations die out. Okay, so in order to maintain A beta equal to 1, this additional circuitry is required over here. And this additional circuitry, how does it works is, so like if this additional circuitry is not there, the internal core is so designed that A beta is always greater than 1. Okay, so what will happen is your output voltage will always start to amplify because A beta is always greater than 1 at whatever oscillation frequency we have. But what happens is, moment this V naught goes higher than this Vx, so moment this V naught, so this V naught is there, and Vx will be something resistor divider between R4 and R3. So R3 divided by R4 plus R3, correct? So moment this Vx goes lower than V1, this diode D1 starts to conduct, and this R4 comes in parallel with R2. Okay, so that makes our A beta exactly equal to 1, and then the voltage is clipped and it starts falling. So as it starts to fall, uh, like uh, as as it starts falling, this after some time this Vx will again be less than V1, greater will become greater than V1, right? So as it becomes greater than V1, again this diode stops conducting, and then R2 again comes in. Like R2 has nothing in shunt with that. So as I said, when nothing is in shunt with the R2, our A beta is always greater than 1. So that's how the circuit works. The moment the oscillation voltage becomes greater than the desired voltage, some either R4 or R5 comes in shunt with R2 and reduces the loop gain and brings the voltage down. While like if the oscillation is within the set limits, neither of D1 and D2 will conduct, and overall our loop gain will be greater than 1 in general. Do you understand this?
Sir, whenever the output voltage is more,
Yeah,
voltage is more, then D2 will conduct.
D2 will conduct, correct. Output voltage is more positive, then D2 will start conducting and R5 will get in parallel with R2. That will reduce the overall loop gain.
Either way, if D2 conducts or if output is low, VO is low,
Yeah, if VO is low,
then
then
then D1 will conduct.
no, no, like if VO is very negative, the magnitude of, you need to understand, we are talking about the magnitude of VO. If magnitude of VO is very high, then what will happen is, as the VO is going on in the positive direction, then it will cross a certain threshold and D2 will start conducting. And when VO is going in the negative direction, it will cross a certain threshold and D1 will start conducting.
Okay, okay,
If the magnitude of VO is low than this threshold, then what will happen is neither of D2, D1 and D2 will conduct, and our A beta will be greater than 1. That will keep on increasing its magnitude till the point it reaches the desired output level of oscillation.
okay.
Yeah.
Got
So, yeah. This was about the Wien-Bridge oscillator. Now other thing is that we had this question over here that like we had a phase shift oscillator and we needed to find out the k for which the system starts to oscillate. So what we were doing wrong last time was that we were taking the loop gain by breaking the loop over here. However, what we need to do is we need to consider this particular inverting amplifier as the part of the loop, and then calculate the overall loop gain and make it equal to 1. We will circle back to this particular problem, or okay, let's start with this particular problem only. So the first order of business is to actually calculate the loop gain by keeping this inverting amplifier as a part of the loop. So what we'll do is we have some V1 over here and some V0 over here, and we will break the loop at this point. If we do that, what we get is we get a low pass filter like this, that is RC. Then we have this non-inverting amplifier that is acting as a unity follower. We have an RC over here.
Sir, here I am having small doubt regarding RC. RC is shifting 60 degrees, na sir? RC combination.
No, yeah. So ideally, all three of them should give. Our main motive is overall loop gain from this point to this point should give a phase inversion of 180 degrees.
Okay, okay. So, how much is the op amp shifting, sir?
No, op-amp will give zero phase shift.
Okay,
This is just a
okay, okay, because it is okay.
yeah,
Non-inverting mode.
yeah. In non-inverting mode, it's behaving as a unity follower, so that will give zero phase shift.
So both the RC, which is both RC combinations, will shift 180 degrees, sir. Is it like that?
No, 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 no. One are like each of the RC, there are three RC combinations,
Okay,
right?
okay. Three,
Each of,
three into 60 degrees. Okay.
yeah, we want each of the RC will give some phase shift, so that overall loop gain from V1 to V out. So this will give just 180-degree phase shift, right? Overall, we need 360-degree phase shift. 180 we will get from this non-inverting amplifier. Rest of it we will get from these three filters over here.
Oh, okay, okay.
Yeah. So then we have this thing over here and a resistor and a capacitor, and this is connected to the, just a minute. So this basically is connected to the resistor, and this is the input resistor to the inverting amplifier. And since the input resistor goes to the virtual ground, so this also can be considered as ground. So we have an RC in parallel in the last stage. Okay. So what will be our So what will be our voltage from, let's say, let's call this V naught, or let's call this V1, and let's call this one as V filter, VF. So first one will give us one pole at 1 upon 1 plus SRC, and then second pole will also give us one pole at 1 upon 1 plus SRC, so this will become squared. And the third one won't exactly give the pole at 1 upon 1 plus SRC, because we have a resistor in parallel with the capacitor. So the transfer function from, let's call this V1 and let's call this V2. So the transfer function VF by V2 will be, so this parallel combination. So what will be the so what will be the impedance of the parallel combination of RC? We will have
1 by 1 plus SR.
1 plus SCR, correct? It's here, right? So we will have this, and on so this will be in impedance division by this resistor. So we will have R upon 1 plus SCR divided by R plus R upon 1 plus SCR, correct? So what we have over here is, so SCR will be cancelled, and we will have R times 1 plus SCR plus R, right? So we will have 1 upon 2 plus SCR. Yes, Suvar, you want to ask something?
No, no, sir. No, sir. Continue, sir.
So this will be equal to 1 by 2 divided by 1 plus SCR by 2. Okay, so overall transfer function from input to this filtering node, that is VF, will be VF by V naught, Vn will be 1 upon 1 plus SCR whole square times zero point 0.5 divided by 1 plus SCR by 2. Okay. So first order of business is to, since this is the overall phase shift that we are going to get, so whatever phase shift we get from this should be equal to 180 degrees, right? So what will be the phase response of this particular transfer function? So from this thing over here, we will have minus of 2 tan inverse omega RC, correct? And the second thing will be minus tan inverse omega RC by 2. So this will be our overall phase response, and this should be equal to 180 degrees, right? So can anyone tell me what is the what is the formula for addition of tan inverses? So we have basically 3 tan inverse. So we have minus of, this should be equal to 180 degrees, minus of tan inverse omega RC plus tan inverse omega RC plus tan inverse omega RC by 2. Can anyone help me write the this summation of tan inverse? Come on, guys, this is basic trigonometry. Can anyone help me with that? So what is the summation of tan inverse x plus tan inverse y plus tan inverse z? No one remembers that. Okay, so we have minus tan inverse. So the expression for summation is, so if we have tan inverse x plus tan inverse y plus tan inverse z, this is equal to tan inverse of x plus y plus z minus xyz divided by 1 minus yz minus zx minus zy. Okay. So the same thing if we apply over here, we get minus tan inverse 2 omega r. So let's write it clearly. Omega rc plus omega rc plus omega rc by 2 minus omega cube r cube c cube by 2 divided by a denominator. So we won't worry about the denominator. So first of all, okay, so this should be equal to minus pi or pi. Okay, so what is tan pi?
Zero.
Tan pi is equal to 0, right? So if tan pi has to be 0, then the numerator has to become 0, correct? Just a minute. Yeah, sorry for the delay. So we have this over here. So what do we have? 2.5 omega rc is equal to omega cube r cube c cube by 2. Correct? Everyone clear till this point? Okay. So omega rc is equal to square root 5, right? And if omega rc is equal to square root 5, so omega is equal to square root 5 by rc. Okay. This is clear? So this is the frequency at which our phase response of the complete transfer function from input to the filter, input to VF will become 180 degrees, square root 5 by RC. Okay, now what we have to do is we need to find out the magnitude response at this particular frequency and then make sure that K times that magnitude response is equal to 1. That's how we will make sure that the system is oscillating. So let's circle back to the magnitude response. 1 upon 1 plus omega square by omega square r square c square. This is the magnitude response of V naught by VF by VI. its whole square times 0.5 divided by square root of 1 plus omega square r square c square by 4. Okay, so let's put this particular omega in this equation. What we get is, so here the this square and square root can be cancelled, so we have 1 plus 5, and r square c square and r square c square will be cancelled in denominator, so we have 1 plus 5 over here, and in this thing we have square root of 1 plus 5 by 4, and on top we have 0.5. So if we simplify this, what we get, 0.5 divided by 6 times 9 by 4, square root of 9 by 4, and square root of 9 by 4 can be written as 3 by 2, and 2 goes on the top. So we have this as 1 by 18. Okay, so this multiplied by gain of the inverting amplifier should be equal to 1. So what is the gain of the inverting amplifier? The gain of the inverting amplifier is minus k, right? So this actually will be minus 18. Why? The magnitude will be 18, 1 by 18, but the overall the gain from input to the filter node will be minus 1 by 18, because we have seen that we see a phase shift of 180 degrees. So overall our loop gain will be k by 18, and this is this is supposed to be 1. So we get the value of k as 18. Any doubt in this? So tan inverse has negative sign because we have so okay, we will do it like this. So let's consider only one root. So we will have, let's say, 1 upon 1 plus src. So if s is replaced by j omega, what we will have, 1 upon 1 plus j omega rc, right? Now like, what do we need to do in order to find out the phase response due to this particular thing? It's basically tan inverse of real part of imaginary part of the complex equation divided by the real part of the complex equation. Now in order to find out the real and imaginary part, this has to be rationalized first.
Sir, up to k equals to 18 understood, sir. What is one? Why we have taken 1 by 1 plus SRC again?
So, we had some doubt from I think Jayakumar S, that why 1 upon 1 plus SRC gives negative sign in the phase response. So that I was trying to.
Okay, okay, okay.
Yeah. So if we try to rationalize it, we get 1 plus omega square r square. So we multiply and divide it by the complex conjugate of this. So we get 1 upon 1 plus j omega rc into 1 minus j omega rc. So we multiply and divide it by that. So this particular term, so a complex number multiplied by its conjugate is equal to magnitude square. So this is a real part, and it is common to both real and imaginary part, right? So the ratio of imaginary part to real part will be omega rc by, sorry, minus omega rc by 1, correct? So like, we will have tan inverse minus omega rc, and since tan is a, or like tan has antisymmetric property, so we will have so tan inverse has antisymmetric property, so we will have the negative sign can come out. Okay, so minus tan inverse omega rc. So if any so if you have a pole, so so to generalize, if let's say you have a pole like 1 upon 1 plus s by p, it will contribute, its phase response contribution will be minus tan inverse omega by p. On the same hand, if you have a 0 such as 1 plus s by z, its phase response contribution will be plus tan inverse omega by z. Yeah. So is it clear? Even no, it won't be right because so what? That's what I explained, right? That if you have a pole, in that case, you will need to rationalize it, and like if you rationalize in the denominator, you will get its conjugate. Correct. So if you get the conjugate, that negative sign will come. Is it clear?
Sorry, here VF by V1, please go to that point, sir. VF by V1.
This one is it?
VF by VI before that step before that one, sir.
Yeah.
VF by VI. No, sir. The starting, sir.
In the starting, you mean the transfer function?
Yes, sir. Transfer function.
Yeah.
VF by VI.
Yeah.
How we please explain this? How we got that 1 by 1 plus SCR whole square into 1.5 by 1 plus
Yeah.
1 by
So
1 plus 1 by 1 plus SCR, because both are same. We have written like that.
correct. So let's go to the circuit over here. So this will give us one pole, that is 1 upon 1 plus SCR, and then it's basically buffered by a unity follower, right? So so there will be no loading between node 1 and node 2 due to the unity follower. And after that, we will get another pole as 1 upon 1 plus SCR. Uh, so at node 3, we will have input transfer function from input to the node 3 will be 1 upon 1 plus SCR
Whole square.
whole square. Correct. The same thing will come at this point also,
Yes.
because again there is a unity follower, and after that we have to calculate transfer function from here to here. Whatever transfer function comes from node 4 to node VF will be cascaded with 1 upon 1 plus SCR whole square. Correct?
Yes.
Okay. So to calculate the transfer function, it might it might be tempting to say that okay, that will also be 1 upon 1 plus SCR. However, like this particular VF node is being loaded by the input resistance of the inverting amplifier.
Yes, sir.
You can see that because in rest two of the filtering stages, there was no load, nothing in parallel with the capacitor. Okay, but in the last stage, the input resistance of the input resistance of the inverting amplifier is loading this particular stage, and since its other terminal is connected to virtual ground, so
We have grounded.
yeah, we have grounded that, and if and then we will have to calculate the transfer function from this particular node to VF, and when you do that, you get the transfer function like this, that is half divided by 1 plus SCR by 2, and that will be cascaded with 1 upon 1 plus SCR whole square.
Okay.
Is it clear?
Okay, sir.
Okay. So now we will solve a few questions of this particular week also. Okay, so the first question is, so we have the circuit over here, what the circuit looks like, what might be its function.
Clamper, I think.
So, what exactly clamper does? Clamper always has a capacitor with it, right? So when the capacitor gets charged, it particularly it clamps to that particular value. You don't have a capacitor over here.
Clipper, sir.
This is a clipper, right? So we need to draw the transfer function of this particular clipper circuit. So how we will proceed? So an easy way. So if let's say you have multiple diodes, in that case, a very straightforward way to approach this kind of problems is that you assume that the input is highly negative first. Okay, highly negative, as in the input is at, let's say, minus infinity. If let's say so I have to draw the transfer function over here, right? So if I assume my input to be minus infinite, which of the two diodes will be conducting?
D1 will conduct.
D1 will conduct, right? Because at the negative end of the D1 there is minus infinite voltage, and at the positive terminal there is minus 1 volt. So the D1 is in forward bias, so it will start conducting, and if this start conducting, and since the voltage drop is given as zero point 0.7, so what will be our V naught? Our V naught will be equal to, this will be zero point 0.7, right? So what will be our V naught?
Minus 0.3.
Are you sure? This is minus 1, and then additional, so this will be minus 0.7 or plus 0.7 from here?
Top voltage and bottom voltage are in reverse, right?
Yeah, so this
P side is positive.
this diode is forward bias, right, in the top direction. So this voltage will be plus, this voltage will be plus, and this voltage will be minus, right? The current will be flowing in this direction, right?
Sir, the notation what you have done is the
Sorry,
current is flowing from. Uh,
current is flowing in the from minus 1 volt to the top side, right?
so
Yes, yes.
signs are also okay, sir. Positive.
Yeah. So in that case, our voltage at V naught will be minus 1.7, right? Because minus 1 minus 0.7.
Yes, sir.
Okay. So as my voltage is as my input voltage is minus infinity, my output voltage will be clamped as my at minus 1.7, right? Now the moment my input voltage, let's say, become equal to minus 0.7, minus 1.7, after that my diode D1 will stop being in
Sir,
forward
I
bias.
have one doubt here.
Yeah,
If diode is forward biased, voltage across the diode will be 0.7, right, sir?
correct.
Then voltage across the diode is 0.7 volts plus negative voltage minus 1.
No, voltage across diode is zero point 0.7, but you have to see in which direction that zero point 0.7 is, right? So let's say my diode was like this. In that case, this would have been plus zero point 0.7. If my current was flowing from positive P side to N side, correct?
There also current is flowing from P to N, right, sir?
Yeah.
Anode to cathode only.
Yeah, current is flowing from P to N, but the P side will be positive and N side will be negative, right?
Yes, sir.
Okay. So this side, so the bottom side will be positive and top side will be negative, right?
Correct.
Okay. So apply is okay. This is 0 volt. Start
Hmm.
applying KVL from this node to the output V naught.
Yes.
What will be this voltage?
Minus 1.
Minus 1 volt.
Uh,
Then what is this is being added or subtracted?
0 minus V1 and minus 0.7.
Correct. So minus 1 volt minus 0 0.7.
0 minus of minus, right, sir?
No. See, this is basically the you have to always be careful of in which what is the polarity over here. When you are going from plus to minus here, so let's say this voltage was some V. In that case, from plus to minus, this particular node will become V, right? And then there is sorry, minus to plus, and plus to minus, there will be a subtraction, right? So our voltage at Vi, it has become too cluttered. Let me draw over here.
Sir, you take three voltages and you apply KVL, sir.
Yeah, correct. Okay. So let's say this is 0.7. This is, let's say, minus zero point 0.8. Okay, initially we don't use any negative sign over here. This is 0.8 and this is 1 volt. Okay. So this is Vi, this is V1, this is V2. Okay. So if you start going from here to here, what will be this voltage? This will be V1 plus or minus.
Minus V1 minus
It will be minus, is it? Are
V1
you
minus.
sure? Okay, so whenever you go from negative to positive, you always add the voltage. So this will be V1 plus 1 volt. Then this will be V1 plus 1 volt. This will be V1 plus 1, and now the polarity has changed. So minus 0.8 volt. And finally, our V2 will be equal to, there will be another plus 0.7 volt, right? So this is how you will apply KVL. Correct? Ravi Kumar, is it correct? Is it clear?
Yes, yes.
Okay. Now let's say I reverse the polarity of this particular voltage over here. What will happen to what will happen now?
Minus 0.7.
Minus 0.7 we will have, not at this node, not at this node. So our V2 will be equal to V1 plus 1 minus 0.8 minus 0.7. Correct? You are clear till this point?
Yes.
Okay. Now let's say I increase this voltage to 1 volt. So what will happen? This minus 0.8 will become minus 1. Clear? Do you follow? Ravi Kumar, I am asking you. Do you
Yeah,
follow?
yeah.
Okay. Now let's say I remove this voltage altogether. So this plus 1 will go away, right?
Yes, sir.
Yeah. Okay. So now what is this? What is this voltage source over here? This can be replaced by this particular diode, right? And if that is the case, we get V2 as equal to V1 minus 1.7. And what is V1? V1 is ground basically, right? So V2 is equal to minus 1.7. Are you able to follow?
Yes.
Do you have any other doubt in this? Okay, we shall move forward then. So this voltage, when okay, we were talking about when Vi is extremely negative voltage. So our V out will be clamped to V out will be clipped to minus 1.7, and the moment our Vi becomes Vi becomes equal to minus 1.7, what and it starts dropping further. In that case, what will happen? Our output voltage will start dropping, becoming less than minus 1.7. So D1 will now no longer be in forward bias. So D1 is open circuit, and D2 has not come yet in forward bias. So both the diodes D1 and D2 will be in open circuit. So Vi will be equal to V0. Correct? So we will have a straight line like this. Till what voltage we will have straight line?
Up to 2 volts.
Are you sure?
1.3 volt.
So okay, when will this diode start conducting?
When anode voltage is 2.7.
2.7, correct?
Hmm.
So basically, you want a diode the voltage across this diode D2 should be equal to 0.7, right? Now, P terminal should be positive. P terminal should have a higher voltage than the N terminal, and by how much higher? By 0.7 volts higher, right? So if this is 2 volt, your output should be at least 2.7 volt in order for D2 to start conducting. So it will go all the way up to 2.7 volts, and then it will saturate. So this is how a transfer function of this particular clipper circuit look like. And any input voltage that is between minus 0.7 and 2.7, we will see it will follow the output will follow the input. But the moment our input voltage becomes larger than 2.7, it will get clipped up over here, and if the input voltage is lesser than minus 1.7, it will get clipped down. So let's say if we had a sinusoid, of, let's say, amplitude 3 volts. So this is my input Vi. How will my output look? It will start following the input. Let's say this is 3 volt. It will go all the way up to 2.7 volt and become constant till the time Vi again falls back to 2.7. Then again it will start following the input. It will go all the way up to minus 1.7 and again become constant. And this pattern will be repeated. So this clipped sine wave will be our output. Is this clear?
Please explain again, sir, this waveform.
The waveform. Okay, so I said my input is a sinusoid. The input to this particular circuit is a sinusoid of amplitude 3 volts. Okay, so what it will do, it will oscillate between minus 3 volt and plus 3 volt, correct? Now as it starts from 0 volts, so we are in this, so let's call this region 1, let's call this thing as region 2, and the extreme right as region 3. So as we start from 0 volt, in which region of operation we are? 1, 2 or 3?
Region 2.
Region 2. So in region 2, the input follows the output.
Output follows the input.
Okay. So the green curve will be overlapping with the pink curve. Now the moment my input reaches 2.7 volt, we will fall in Which region?
Clip on.
Region 3, right?
Yes,
Region 3. So in region 3, no matter what my input is, my output will always be stuck at 2.7 volt.
yes, sir.
Okay, so my output will be a flat line till the time my input again comes back to for 2.7 volts. Is that clear?
Yes, sir.
Okay, now same thing will happen on the other side also. So the output will be clipped on positive side at 2.7 volt and negative side at minus 1.7 volt.
Yes, sir. Got it.
Okay, so let's move on to the next question. So this is a straightforward question where we are asked that common emitter transistor amplifier. So let's say we have this. We have some biasing voltage plus some current, some input, and the VDD is set such that my current, my collector current is said to be equal to 1 milliamps. My base current, when its base current is 25 milliamp at room temperature, its input resistance is approximately equal to. So how do you calculate the input resistance? What is the formula for input resistance of a BJT? That is the formula for the input resistance of the BJT. What is the input resistance? It's the base resistance that is looking into the base side, right? Okay, so whatever looking in resistance from this side, let's call this R pi or RP. So RB is equal to VT by IB, correct? Now VT has been VT is the VT at room temperature has been given as 26 millivolts. So we have 26 millivolts divided by, wait a second, when its base current is 25 milliamps at room temperature. The collector current is given higher in this question, lower in this question than the base current. That shouldn't have happened.
It may
I think it
take it
is
as
25
25 micro.
micro.
Yeah, yeah, okay, this should be 25 micro. So in that case, our base resistance will roughly be equal to 1 kilo ohm, right? So this is 10 to the power minus 6, and in numerator we have 10 to the power minus 3. At the end we will have 10 to the power 3. So, and 26 by 25 is roughly equal to 1. Okay. Now this question over here, so we have been asked that, so we have studied three configurations of BJT, right? Common base, common collector, and common emitter. And input resistance has been asked. So basically we need to arrange these three configurations in the the ascending order of the input resistance. So let's try to draw all three of them. Okay, I will draw three circuits. You tell me which is common emitter, common base, and common collector. So here is one circuit. Here is another circuit.
For CC is high, and for CE is moderate, and CB is low.
Okay. So first thing over here, can you tell me which is, so circuit 1 is, what is my circuit 1? Out of common collector, common emitter and common base, which is my circuit 1?
One is emitter, second one is base, third one is collector.
Common emitter.
This is common emitter, circuit 2 is common base, and third one is of course common collector.
Collect.
Okay. So in this case, in the first case, so you guys know the small signal model of the transistor, right? How the small signal model of BJT looks like? So if this is, this side is base, we have RB over here. This is my emitter. N times VBE, and this is my collector. Okay, so this is how my model of transistor looks. So if I replace the model in all the three circuits, how will the first circuit look like? RB, we have VB, and emitter is grounded. This is GM times, since the emitter is 0, so GM times VB. This is collector, and there is some resistance over here. Okay. My second circuit will look like, Subarao, can you mute yourself if you don't have anything to say, because there is some disturbance. Yeah. Thanks a lot. RB, or this is some, let's say, I in current, and this passes through a resistor. And my third circuit looks like, so third circuit is common collector, VB, this is emitter, and this is some other resistor, and this is GM times VBE. So what is the looking in impedance from this side? The input impedance in common emitter stage, what is it? So it's only a resistor RB connected to ground, right? So Rin we will have over here is equal to RB. Now what happens on the other side? In this particular case, the looking in impedance will be from the emitter side. Correct? So let's give a test voltage in this case, V test. So if this is V test, what will be the current flowing in the on the base side? It will be V test by RB. And what will be the current flowing in this direction? So current flowing in the downward direction is GM times VBE is equal to GM times VB minus VE. Now VB is equal to 0, so it is minus GM times V test, because V is equal to V test. So this is equal. So current flowing in the towards the collector will be GM times VT. So our I test is equal to V test by RB plus GM times V test. So our looking in resistance will be V test by I test. This is equal to, what is it equal to? RB upon 1 plus GM times RB. Now if GM times RB is significantly greater than 1, then this will be approximately equal to 1 by GM. So GM of a transistor is very high, so this particular voltage will be an extremely low voltage. Is this clear?
Sir, GM BB is equal to GM into BB minus V you have written.
Yeah,
Then it is you have written minus GM into VT.
correct.
How it is? Sir?
So what is the value of VB? The base voltage is grounded, right?
Yes, sir. Yes, sir. Yes, sir. 0. Okay.
Yeah, 0. And VB,
Okay. Test voltage. Okay. Okay.
yeah. Okay. So is this derivation clear? Okay. So this is done. Now the final thing, that is our common collector configuration. So again we will apply a test voltage at this node. Let's call this V test. So what is the current flowing in the current flowing from the test voltage? IT is equal to VB minus VE by RB. Now VB is equal to V test minus VE by RB. Okay. Now we need to find out VE in terms of V test, so that we can overall find out the the current that is flowing through this voltage source. So what is VE? So VE will so basically two currents are flowing into this emitter terminal, right? So what two currents are flowing? That is IT plus GM times VBE. Okay. So if we replace that, VB is equal to VT, right? So VT minus VE by RB plus, again this is also VBE, right? So VT minus VE times GM. This is the total current flowing into this resistor, right? And what is the current flowing from this resistor towards the ground? This is equal to VE by R. Okay. So if we equate that, we have VT times 1 plus GMRB divided by RB is equal to VE times 1 by RB plus 1 by R plus GM. Is it clear? So this 1 by R plus 1 by RB is basically the expression for parallel combination of RB and R. So we'll write it that way. 1 by RB parallel R plus GM. Okay, so finally our VE is equal to V is equal to RB parallel R divided by RB times, we have RB parallel R divided by RB times 1 plus GM RB divided by 1 plus GM RB parallel R. Now it can be assumed that since GM is a very high quantity and resistances are also very high, so GM times R can be assumed to be much larger than unity. So 1 plus GM RB parallel R and 1 plus GM RB can be approximately equal to 1 plus GM RB parallel, GM RB parallel R and GM RB respectively. So if we do that, we get RB parallel R divided by RB times GM RB divided by GM RB parallel R. Okay, so GM will be cancelled, RB will be cancelled, and RB parallel R will be cancelled by RB parallel R. So this is roughly equal to 1. So our emitter voltage is approximately equal to unity. Okay. So so our emitter voltage is equal to the input voltage. The gain is equal to unity. So and you might have heard, right, common collector amplifier is also known as unity follower. You have heard this term?
Voltage follower.
Yeah, voltage follower or unity follower. Okay, so basically what happens is, however my VI is swinging, in the same fashion my VE is also swinging. In that case, what will happen? If VI or V test is equal to VE, what will be the current flowing? What will be my I test?
Zero.
I test will be approximately 0. Why? Because my V test is approximately equal to VE. If my I test is 0, what is my resistance?
Infinite.
Okay. So common collector has roughly, so Rn is tending to infinity. So common collector has the highest resistance. Common emitter has a resistance equal to base resistance. This is also very high, but not as high as common collector. So common collector basically has this RB multiplied by some quantity which is approximately a very large number. So Rn is almost infinity. And common base is having 1 by its resistance as 1 by GM, and since this GM is very large, so it virtually has a very small resistance. Okay, so Rin of common collector is greater than Rn of common emitter is greater than Rn of common base. Is it clear? Okay, so this was it from my side for today's session. Any other doubts?
I have doubts regarding filters.
Okay.
Filter assignment questions. Week 7.
filter assignment question. I don't have the assignment as of now. Can you please share your screen and present the assignment?
Yes, I'll share.
Yeah, sure.
The tan inverse how? Oh, sorry. The tan inverse two terms. First term is also correct. The tan inverse
Yeah, tan inverse.
minus tan inverse
So I explained that, right?
minus tan inverse first term is no sir I didn't understand.
Okay, we will get back to that once this the Ravi's doubt is clear. We will get back to that.
Yes sir.
Okay, which assignment you are talking about?
Week 5 shares filters.
Which question?
First one, two, you explain all this, sir.
Explain all these.
Yeah, yeah. I did not understand how they are solved. They are given in solutions, but I did not understand that solution.
Okay, so a filter is having.
And in this, they did not mention whether it is Butterworth or Chebyshev,
Okay,
and
let us see.
that is low pass or high pass also not mentioned.
A filter having almost constant magnitude in passband or transmission with a variation of -6% to +6%. The magnitude of stop band transmission is at most 1%. Uh, well, this is a very ambiguous question. I don't know what does this mean. What is Amax? What is 6%? What is -6%? I mean, I don't think these kind of questions you will see in exam, man.
But this assignment also considered into evaluation, right, sir? At the end,
No, that's correct, but you can basically
even in lecture also they did not explain regarding these things.
hmm.
Similarly, all these questions they are asked what is the order of the filter. Butterworth filter they are given something uh, pass band frequency and stop band frequency, and they are given Amax, Amin, and they are asking what will be the order of the filter.
No, like in lecture, do you have these expressions of Amax? What is Amax? What is
No,
Amin?
no, 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 sir. In lecture, they are explained simply low pass and high pass and filter conversions.
No, but then I think you should record this, because I can clearly see that.
I think they have
In
explained in the
forum also,
tutorial.
I posted these questions, but they are not given solution. And early at
Tutorial
your problem solving session, I attended one more. There also, I did not find the solution.
in tutorial they have given this. They have solved this type of questions. So, please verify. I have seen. You also please verify.
Okay, just looking at these questions, I also can't understand anything. I mean, these are like I don't think the questions should be framed like this, and I am certain that these kind of ambiguous questions won't come in exam. So, yeah. Okay, so any other doubt? Jaya Kumar, you were not able to understand that minus tan inverse omega RC, is it? Okay, I think Jaya Kumar left the meeting, so
I have doubt regarding
yeah, tell me.
in the question they have given uh, current in GNR question. They have given. I am not asking a solution, but I am not getting any clarity about this one. So they have given the knee current. This is some 500 microamps, and they have given the GNR current IZ 2 milliamps per some test. They are saying that it is a test current, and for some VZ, like that they have framed the question. So are the shall we take the V knee current, knee current as I minimum and IZ minimum, and the current they have which they have given as IZ max. Is it like that?
Do you have, so is there a figure with that? Like, can you share the figure?
One second, sir. Sir, this one, sir.
Okay, so this EZ naught is said to be 4.9 volt. The test current is 2 milliamps. The some test voltage at test voltage test, then current is registered here. Current is given as. So what exactly they are asking in this question?
They are asking the output voltage,
Can you scroll up a little?
sir. Okay, okay, one second. Is it now visible, sir?
Yeah. So, here, basically, what they are trying to say is that so they have given a, VZ and this thing, right. So, ideally, what we assume is that Zener voltage has Zener diode has zero resistance. So, based on this VZ and IZ, you need to find out what is the RZ that you will get and replace that particular thing with the circuit. Come down once.
RZ they have given, sir. One second.
Okay, VZ naught is equal to 4.9 volt. Uh, VZ naught has been given as 4.9 volts. IZ has been given as 2 milliamps. At interest voltage VZ. Okay, knee current is given as. I don't think knee current is important over here. So you have been given RZ. You have been given. Wait a second. Mm, You have been given RZ over here, and it's 50, right? Okay, so it's just that you need to replace this circuit replace the equivalent circuit of the Zener diode with the RZ and BZ not given, and calculate the output voltage for various RL, right?
Okay,
Okay, so BZ not, whatever Zener diode you have, you replace it with this VZ
equivalent.
in series with RZ that has been given, and then so with, for various RL, calculate the output voltage.
Okay, okay, okay.
Okay, any other doubt? Okay, so let's come to your minus tan inverse omega RC. So, were you able to understand that? So, what exactly you are not able to understand? That how 1 upon 1 plus by gives you tan inverse omega.
Yes, sir. Two terms there, denominator. How did you take
Sorry,
only one term? Two terms there, sir, in denominator. How do you take only one term?
two terms are in this. So, you are talking about this particular expression only, right?
Yes, sir. Yes, sir.
So, what we do is we will go procedurally over here. So, first of all, you have to replace S by j omega. You understand this, right?
Yes.
So, we
Yes.
have 1 plus j omega by p. Okay. Now what is the phase response? Tan inverse of imaginary part by real part. Correct?
Sir, your screen is not visible.
Yes.
Is it
Oh, just a
for me
minute.
or all?
Uh, is it visible now?
Now it is visible, sir.
Yeah. Jayakumar, where exactly you had the doubt? You are you able to understand that the phase response of 1 upon 1 plus s by p will be minus tan inverse omega by p?
Yes, sir. Yes. I understood that, sir. But why did you take, when you take conjugate, why did you take only second term?
Just a minute. Over here.
Yes. Yes.
So only second term. So basically, what will happen is this is so 1 upon 1 plus j omega RC will be multiplied and divided by its conjugate. So how will it look like? 1 minus j omega RC divided by 1 plus omega square r square c square. Correct?
Yes. Yes.
Okay. Now when you so if this is written as RE plus j times IM, what is your RE?
One.
No, it's 1 upon 1 plus omega
One.
square r square c square, right?
Oh, yes. Yes. One.
And your imaginary
Yes.
part is minus omega rc divided by
Minus
1
j
plus.
omega by omega square r square c square.
Okay, so what we will have is tan inverse. Now uh, we need to take the ratio of imaginary part and real part. So the denominator will get cancelled out, right? So we will have minus tan inverse minus omega rc, and since tan inverse is an antisymmetric function, so minus can come outside. So we will have minus tan inverse omega rc. So this is how you get negative in case of poles. Is it clear?
So in all poles, we'll take minus tan inverse.
Correct. All the poles will have minus. No. All the left half poles will have
Left.
minus tan inverse. Right half pole will have plus tan inverse. Because in that case, here instead of plus, you will have minus.
Yes. Yes.
Okay. So all the and right half zeros will have minus, and all the right half poles and left half zeros will have plus.
Okay. Okay.
Okay. So is it clear now? So if there is no other doubt,
Yes,
this
sir.
was it
Yes, sir.
from my
Yes, sir.
side. Thank you for attending.